talk at all anymore. It's beautiful.
Good afternoon. Welcome to the Bloomington Rotary Club's weekly celebration of service. I'm Steve Wicks, and I'm honored to cover for this year's president, Tracy Jovanovich. In honor of President's Day, we'll start our session with a Pledge of Allegiance. Please stand if you're able. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Our thought for the day is from Phil Emerson. Navigating change is hard and uncomfortable. It's important that we maintain tough minds, soft hearts, and strong hands in order to drive the best possible outcomes. Tim Thrasher has a reflection for today.
Thank you, Steve. First, I need to start with a disclaimer that the tiramisu is so darn good, it's ruined my concentration. So if this goes badly, it's the tiramisu that caused the problem. I'd like to thank President Tracy for the opportunity to speak here and just say briefly that I think it's a wonderful idea to have past presidents speak about accomplishments of the club from previous years. Gives new members a real opportunity to learn more about the club, and members of a little bit longer standing, such as myself, an opportunity to have our memories refreshed about the club's accomplishments. I'm not going to speak about my year today. I'm going to speak about the year that Brian Price was president. Now, Brian was president during the 2002-2003 Rotary year. And I've known Brian for a long time, many years, and always considered him a wonderful friend and exceptional club president. And it became difficult for Brian to make the commitment to attend regularly here. So he made the very difficult decision to terminate his membership not too long ago. I'd like to try to help our newer members become familiar with some of the accomplishments that took place during Brian's year, and also help some of our more long-term members, such as myself, recall some of the accomplishments from 22 years ago. It's hard to believe it's been 22 years. During Brian's year as our club president, our club's accomplishments included record-setting contributions for our club to the Rotary International Polio Plus program, selection of Reverend Ernest Butler as our club's first recipient of the Service Above Self Award. And I would add that that award was presented by then District Governor and member of our club, the late Judge Randy Bridges. Bud Core was honored as our club's first 4 Avenues of Service Award recipient. Our club sponsored an outgoing ambassadorial scholar. We hosted an incoming group study exchange team from Nigeria. And the club conducted a significant push to add Paul Harris Sustaining Fellows to our club's membership as contributors to the Rotary International Foundation. That program, you may recall, is called Every Rotarian Every Year and encourages all Rotarians to make contributions to the Rotary International Foundation on an ongoing basis. We were able to add 18 new contributors that year. Brian's year truly was a remarkable year, and he was named the Rotary Club President of the Year for District 6580. Thank you.
Thank you, Tim. Sam Udek will introduce our guest today.
Hey, we only have a couple guests today in-house. We have Nicole Helms, who is a guest of the club, Minka Wiltz, a guest of Connie Shuklis, Diego Barbosa Vasquez, guest of Alon Barker, and Yaya Cater here with Rotaract. And Joy, do we have any guests online?
Hey, why, yes, we do. We have Megan Gerhardt, who's not really a guest, but yes, she is, joining us from the Czech Republic, right? And you have watching us from a room with a space heater and 8 other flatmates because it's really cold where they are and they don't have heat in their place. More information than you wanted, but there you go. And also joining us is Tracy's husband, Vlad. He is online. I'll say, am I missing anybody else? I don't think so, other than Katie Cerniak, who is one of our new members, is on Zoom for the first time. So welcome to her on Zoom. That's it.
Welcome, everybody.
Welcome guests. If you'd like to learn more about Rotary, please turn and ask the person next to you. We'd love to tell you more. Birthdays. We have 2 birthdays to celebrate. Both Kyla Cox-Deckard and Jim Cryway are celebrating their birthdays today. And then we have 1 anniversary, Jeff Bradley, for 11 years. In terms of announcements, we have, for the rest of this quarter, we have quite a few empty slots to fill for meetings. So we need your help in filling these slots. Lots of different possibilities. And Natalie will resend the sign-up sheet, and thank you. And then Sarah Laughlin has a very important Community Services Committee announcement.
Or maybe 2. So the first one is, I think you've seen this already in the roundabout, but I just want to ask you again to consider volunteering for our Hoosier Hills Food Bank Winter Food Packing Day. It will be Friday, February 28th, and we have 2 shifts, 10 to 12 in the morning. We have 8 people signed up for that one, and we need 15. And the second one is noon to 2, and we have 3 people signed up, and we need 15. So we need a lot of help from you on those, just those 2-hour shifts. Maybe you can take a long lunch hour. Maybe you know somebody else who would like to volunteer. Maybe the Rotaract people will show up. Yeah. And so it's always a lot of fun. It's a project our club has done, for many years, and we always have a really great time. So don't miss it if you can possibly show up. You'll see the sign-up genius in the roundabout. I brought the sign-up sheet today, so if you want to just tell me, sign up today, catch me before I leave. The second one is an annual opportunity from our club. We have the opportunity to apply for a district grant. The district will match our $3,000, so it's a $6,000 grant ultimately. You have on your table 2 pieces of information to make a proposal to be the district grant awardee for a nonprofit in Bloomington. Any nonprofit in Bloomington, you must have a Bloomington Rotary sponsor. You must have one of us say, yes, I'll sign my name on your form. That's all you really have to do. You don't have, there's no work involved in being a sponsor, but we're counting on you to help us get the word out to your favorite nonprofit. We figure that everyone in this club is either works for a nonprofit, is on the board of a nonprofit, is a big supporter of a nonprofit, has benefited from a nonprofit. We know the nonprofits in this community, right? So please help us get the word out to them. So the yellow sheet that's on the table in front of you is kind of your instructions about what you can say to the nonprofit when you ask them if they would be interested in working with us on this proposal. And the white sheet, which has a front and a back, is the form that they need to fill out to send to us. Usually the proposals are a couple of pages, just a Word document, couple of pages. And the hardest thing for them we found, I mean, any nonprofit can use $6,000, right? That's not a question. The hardest thing we found for them is they need to tell us how they will involve 25 Rotarians in a day of service. And that's sometimes hard for them to imagine. So you can help them with that. Describe the ways we've helped other people, from baking brownies to, trail maintenance. And we can, and the other thing I want you to know is that we don't actually get approval to start spending the money until about the 1st of August, the first week of August usually. So the proposals are due to us by March 28th. We will work with the winning nonprofit to submit the proposal to our district by May 1st. And then there's kind of a wait while we wait for it to go be approved at the district level and also at RI. So the project has to happen between like the middle of August and March, the end of March, which is not a whole year. And it's mostly winter. So think about that when you're making your proposals. Probably best not to have something that you need to start on August 15th, because there'll be a really quick turnaround for us if that happens. So thank you very much. I'm going to put the proposal form and everything in the roundabout, so it'll be there in case you want to, send it to people, or you can just email me and I'll be happy to send you the document if somebody wants to fill it out. But your job is to help people be nominated. 700 nonprofits in this community. I think the most we've ever had was 12 proposals. So let's beat that this year.
Thank you, Sarah. So deadline, March 28th. Let's generate some great proposals. I think we have time for happy dollars. Is anyone out there happy? It's kind of a quiet crowd today.
Anybody online? So I don't know whether this is going to be good for me, but I'm going to give $20 because I'm happy I didn't slip on the ice so far today. So we'll see what happens with the rest of the day. So.
I've got
Steve, I'm
$500
Raj.
because I found a parking spot.
Okay. Steve, I'm Raj.
I'm happy because I'm here. And I've read now a couple of articles and listened to an interview at NPR a couple Saturdays ago. And it said how important it is during this time of significant change to find joy. And you do that through family, friends, and community. And so for me, I'm here despite the icy weather, Alain, and the potential to fall, but this brings me joy, and I want to give 50 happy dollars to my joyfulness. Thank you.
Steve, we do have some contributors online. We have Caleb Poer, who has donated $5 for his art project or installation up at the Indy Airport. And then Raj, you wanted to contribute. Say something.
Well, good morning, fellow Rotarian. I'm very happy to join you on Zoom. It is cold and icy, as well as in Bloomington, So it's so nice to see us all fortunate enough to be nice and warm and visiting with each other in a lovely day like today. I give $20 for the occasion.
So I am very happy that my driveway just blew right off today. It didn't stick or anything. The leaf blower was wonderful.
Well, I guess I'm not that happy, but here's a couple bucks for, I'm just glad spring's coming.
I have $20. I am happy that I can think about spring. The track and field season has started and my youngest is going to be participating at Bloomington High School North.
It's got to be the most weather-related one ever.
Spring training is underway in Arizona. $10
For spring.
Well, it was slow getting started, but we actually have a lot of happy people in the room here.
One more?
Oh, one more.
We have Tim online too, please.
Making a donation here just because I'm happy.
And one more online.
I guess this relates to the weather. I want to share some happy dollars for the First Christian Church, First United Methodist, who have been opening in this very, very cold weather an emergency shelter. I can't remember all the names and initials of it, but it's been serving a real purpose to people that are unsheltered and unhoused. And hats off, I'll say Sherilyn Gershon and other workers that are keeping the shelter available during these cold nights for people who otherwise would be out in the cold. Thank you.
Thank you all for your generosity. And now Connie Shakalis will announce our exciting program for today.
Thank you, Steve. I am really excited because this summer, I met the woman who I always wanted to be when I was her age. I wanted to be an astrophysicist. So did Anne Bright, by the way, but unfortunately, in my case, I don't think I was smart enough. So Yaya, hello, welcome. And Jeff, I am going to give you some joy in a moment or two. Neutrinos are fundamental particles with no charge and very tiny masses. Correct me later if I'm wrong. These mysterious and elusive particles, in the words of Stephen Hawking, are the most abundant particle in our universe. A neutrino's mass is almost zero, which I hope you will ask Anna about, mass having nothing, less than nothing. Physicist Anna Reine worked way underground in gold mines. She lived in New Orleans and witnessed the destruction of Hurricane Katrina. She started out in English Lit. She recently at IU taught electricity without ever having taken the subject. She's super smart. I met Anna at a haiku workshop last summer. Yes, she also writes poetry. As I found out, does my guest, Minka Wiltz, who gave me a book today. She won the Emily Dickinson Award for this book of poetry she wrote. Someone once said, actually my husband Gus told me this, that if you want to understand the meaning of life, start out as a physicist and end up as a poet. Anna did in reverse. Anna Reine.
Thank you so much, Connie, for that wonderful introduction. That was really lovely and generous of you. Yeah, while they're getting this straightened up, I'll just say that I'm really excited to be here talking to all of y'all today about this topic. Oh, okay. We'll give it a moment then. Okay. Test. And if you need me to, I can go stay by that microphone. Test. Okay. Sorry. about
Sorry.
that. Too much hair.
There you go.
All right. Hello, test 1, 2. Well, it was worth a try. I don't know what I'm doing here. Okay, good. Wonderful. Okay. Then I will go ahead and get started. So thank you to Connie for that great introduction, and thank y'all all for having me here today. I'm really excited to talk to you about the work that I do. And I just want to say to start off with, I know from experience that when I tell people I'm a physicist, sometimes they're really interested and excited, and sometimes they kind of want to run away, which is fair. I know mathematics is the language of physics, and people can find mathematics intimidating and have had all kinds of educational experiences, good and bad, with physics. So part of my point of talking to you here today is to kind of share the perspective that I have, which is that science and physics in particular are for everyone. And the sense of wonder and awe that they can give us about the universe shouldn't just be for those of us who do the research on them, but should also be shared with the public. And that is one of the beautiful things that science can bring into the world, just like art or poetry can. And so to talk about that, I want to talk about the research that I work on, the kinds of questions that my collaborations and I think are interesting to explore, and the kinds of novel techniques that we have to use to try to get in, to find out about them, some of which Connie already brought up to you. So one of the questions that I want to try to think about in my research is, why are we here? Which is obviously a huge question, and not one that I am under any illusions about being able to completely answer, or have my colleagues and I completely answer. But there's one particular element of this that our research touches on that I think is fascinating. So first you might ask, what do I mean when I say we in this context? Am I talking about humanity or life? And I'm going more basic than that. I'm talking about the stuff of the universe, which is matter. So everyone here will have heard of atoms, which are made up of electrons, and then a nucleus that has protons and neutrons. And those protons and neutrons are actually made up of even smaller constituent particles called quarks. And there are more examples of matter particles, one of which, the neutrino, we'll get into later. But one of the questions we want to understand in my research is, how in the current universe did we end up with all this matter? And so one way to think about this is to kind of go back and think about the history of the universe a little bit. So scientific theories right now believe that at 13.8 billion years ago, we had the Big Bang, where we had this period of rapid expansion in the universe. And that happened within really a fraction of a second. And still within the first second of the universe, in this really hot, energetic environment that we had, we started to get neutrons, protons, and electrons forming. And eventually, as things expanded out and cooled down, we got nuclei forming, and later on full atoms. And then eventually, as things cooled and expanded some more, you started to get periods of the universe that were a little denser than others, where gravity caused matter to collapse in on itself into stars. And in the stars, some heavier elements were able to be born. But I'm going to be focused on really kind of this early part with the neutrons, protons, and electrons forming. And I want to tell you that that is part of the story, but there's actually another piece of it that happens at that same period, which is that when that matter was starting to form, so too was something called antimatter. So what is antimatter? Well, every matter particle will have a corresponding antimatter particle or antiparticle that has the same mass but opposite electric charge. So these are called things like positrons or antiquarks. And so to go back as an example, you can compare the electron and the positron. Both are the same wildly small mass of around 9 × 10⁻31 kilograms. So that's 31 zeros, hard to conceive of. But while the electron is negative, the positron is positive. And so that tells us kind of what it is, but with everything in physics, you want to know what it does. And so if you want to know how antimatter interacts with itself, it's pretty similar to how matter does. Just like 2 electrons would repel one another because they have the same charge, 2 positrons would also repel one another. But the more interesting question to ask is, what happens when matter and antimatter get together? And when they do, if they collide, they do something called annihilate, which means that the matter and the antimatter disappear into energy, these particles called photons that are light particles, essentially. And so instead of having matter and antimatter, you just have energy coming out. So this is really interesting. So there are processes that create positrons in the modern universe, but they don't stick around very long because there's all these electrons everywhere. And so they'll just immediately annihilate and release just a small energy burst. And so this brings up the question of, well, the universe that we're in today, there's all this matter and there's not antimatter to balance it out. And this is true on Earth, but that's also true kind of at every distance scale that we are aware of. Like this is true in the Milky Way and just at the universe at large, that pretty much everything is just matter. And we think that at the Big Bang, matter and antimatter should have been created in equal proportions. And so somewhere down the line, we ended up with an asymmetry. And even though the universe today is really heavily matter dominated, it didn't have to start out that way. In fact, in the early universe, we just have to induce this really tiny imbalance where for every billion antiparticles, you need 1,000,000,001 matter particles. And those billion particles and antiparticles meet up and annihilate, and everything in the modern universe is just coming from that extra one particle that out of every billion, which is wild to think about. And really fascinating to try to understand. And part of the reason that this is confusing is because the processes that we know of tend to respect this sort of underlying symmetry of the universe where matter and antimatter tend to be created and destroyed together. So the example that I gave before with electron-positron annihilation, you had started off with matter and antimatter and ended up with none, but the relative amounts don't change. And same with the process of producing them in the early universe. We can have very energetic photons that collide and give birth to an electron and positron, but we've got one matter particle and one antimatter particle. So the balance hasn't shifted at all. So this is kind of what I'm interested in looking for, is processes that shift the balance, not necessarily the exact one that would do so in the early universe, but ones that had the possibility of it. Because we want to know, how do we create an asymmetry? So this is what I'm interested in, is looking for an hypothesized process that is a variation of a much more common and well understood process that is called beta decay. And if you want to think about what beta decay is, you can think of it as kind of a spontaneous alchemy of sorts. It's where one element can change into another element. But you don't get lead changing into gold or anything like that. It's only certain elements that can change into certain other ones. And it just kind of happens on its own at well-defined rates. But the version that we're looking for, if it exists, would be a lot rarer and more complicated. And so in this process, in my case, I'm looking for it in an element called germanium, and specifically in the version of germanium that has 76 protons and neutrons, which is definitely a simplified picture. And we want to look for the process wherein in that nucleus, you have 2 neutrons change into 2 protons, and you have 2 electrons being emitted. So you've got electric charge being preserved. You get started with 2 neutral things, end up with 2 positive, 2 negative. But you start out with the amount of matter particles in the nucleus, and you still have that many matter particles in the nucleus, but you've created these 2 extra matter particles, the electrons, and you have no antimatter that balances them out. So this is what we're looking for, because this has created an imbalance. We've created some matter without creating corresponding antimatter. And this is a thing we can look for. You can build detectors out of germanium, and that is what we do. And these 2 electrons together should have a combined energy that we know. And so we just go look for things that deposit that amount of energy and see if we see an excess there. So that's what we're doing. What's the challenge here? What's the problem? Well, for one thing, we haven't seen it yet, which is not so surprising. If this does exist, it would be very rare. I'll get more into that later. But the other thing is that this is not something that is allowed in the standard model of particle physics, which is the model that describes the best of our knowledge so far of physics at the particle level. And this is something that's very interesting. This is because the standard model tends to respect that thing about matter and antimatter being created or destroyed together. But as much as this is a challenge, it's also an opportunity, because the standard model is a great model. It's had wonderful predictive power, but we know that it is incomplete. There are things about the universe that it can't explain. So we are looking for deeper theories that help us understand physics beyond the standard model. And so finding a decay like this would help us understand, how to build better theories that encompass more aspects of the universe. So this is part of what we're looking for when looking for this, is not just to understand the matter-antimatter symmetry or asymmetry, but also to understand potential physics beyond the standard model. And in this case, this physics wouldn't change the particles involved in the standard model, but it would change one of the properties of a particle called the neutrino. And you can see there are 3 types of neutrinos here that are indicated with this Greek letter nu that looks kind of like a V. And we're just going to focus on the electron neutrino today and not get into the other ones. Now, it kind of seems strange to say that this process is related to a neutrino when I didn't show any neutrinos at all, and I'm going to get to that later. But first, we'll kind of remind you what Connie was telling you about earlier, which is what even is a neutrino in the first place. So let's go over some of the properties. The word neutrino means little neutral ones in Italian. And so these, unlike electrons and positrons, don't have electric charge. They are, as was mentioned, highly abundant. So most of the neutrinos on Earth are coming from the sun. And the statistic that I like to share about them is that every second there's 100 billion of these things passing through your thumbnail. So they are everywhere. It's wild, which leads to the next point, which is that they really don't tend to interact with matter. You've got all these neutrinos passing through you, and there's a pretty high chance that none of them will interact with your body in your whole lifetime. And if they do, it's harmless, like it's a very mundane kind of interaction, but that's just to give a sense of like the scale of these things. Sometimes they're called ghost particles because of that property of just passing through stuff. And so like the neutrinos from the sun, most of them will just pass straight through the Earth without interacting with anything. And if you wanted to actually like create a neutrino shield and shield even just half the neutrinos from some source, you would need about 6 trillion miles of lead. So not a feasible thing you can do. You can't shield neutrinos. It's not a doable thing, which is fine. We don't need to. But that sets kind of what experiments look like for these things. And then the other property, as was mentioned, is that they are very light. I mentioned earlier how light electrons are, and neutrinos are at least 100,000 times, probably at least 1 million times lighter than those electrons. They're the lightest thing that we know of that still has mass. And so this is another really interesting property of them. And it's another one that is compelling because it's something that the standard model didn't actually predict about neutrinos, was that they would have mass. So that's another hint that neutrinos might be something that's going to tell us something about physics beyond the standard model. So the property of neutrinos that are relevant for the decay that I'm looking for is a question of whether neutrinos are their own antiparticles. And this is possible with neutrinos where it wasn't with something like electrons, is because they're electrically neutral. So the opposite thing would also be neutral. And the symmetry breaking decay that we're looking for from before is only possible if neutrinos are their own antiparticle. So that's another interesting thing we'd find out right off the bat. If we see this decay, it would tell us something about neutrino properties. And I'm not going to go into detail about why that is, but just to kind of give a hint of it. So this is the decay I mentioned before that we're looking for. There's a corresponding decay that kind of goes along with it that is allowed in the standard model and that we have experimentally measured very well, where in addition to these 2 electrons being emitted, we also have 2 antineutrinos being emitted. So you basically keep the same balance where you have 2 matter particles and 2 antimatter particles being emitted. And so even though in this process you have no neutrinos that we can see, sort of in the, like within the nucleus, there are kind of interactions involving neutrinos that allow this to happen where it wouldn't be allowed in the standard model. So neutrinos become important even in this thing where we don't see any neutrinos, which is kind of interesting and hard to explain. So that's kind of the why we're interested in looking for this. So now I kind of want to get into a little bit of the how. But when I talk about the how, I want to talk about what the challenges are. And one of these is the point that I mentioned before, which is that if this happens, it would be incredibly rare. And to say how rare, we can give this figure that the half-life of this decay is greater than 10 to the 26 years. So let me break this down, what the statement means. Half-life is the way that we characterize how long decay takes on average. This is kind of a random process that's true for any sort of decay process. So if you have a bunch of atoms, it's the time it would take half of them to decay. Or if you've got one atom, it's the time it takes to have a 50% probability of decaying. This 10 to the 26 years sounds impressive, but to get a scale of how impressive, we can compare it to something else, which is the age of the universe that I mentioned before is 14 billion years old. And so we're looking for something that is way longer than the age of the universe, which is weird, right? Like, how would you even find something like that? And the way that you get around it is to find something like this, you would have to have a ton of atoms. If you have a ton of atoms, then there's a decent probability that one of them will have interacted like this, even though for half of them to have done something like this would be longer than anything that could conceivably, not even conceivably measured, like that is possible to measure. And luckily, you can get a lot of atoms pretty easily because there's a lot of atoms even just in like a kilogram of matter. But still, to kind of get to the scales that we want to, which is even far beyond this, the experiment that I'm involved in, that it's sort of the next generation of experiments, which is called Legend 1000, it's going to use a ton of germanium, and something like that would have like 10 to the 28 atoms. So you can see that now we're starting to get large numbers of atoms that are kind of ballpark, what we need. But even with that, you would want in this experiment to be able to run this ton of germanium for 10 years. And for what we're interested in, you might still only see 3 or 4 decays in that 10-year period. And that's the signal that you're looking for, which makes it a really challenging problem, not just because of how rare this is, but because of something called backgrounds, which is there are other things that can deposit energy in your detector too. And if any of those things look like the thing that you want to observe, then you can easily swamp out 3 or 4 decays in 10 years. It's going to be no way of distinguishing. And so this really sets the challenge of building an experiment like this, is how to build an experiment where you've got plenty of mass, but the backgrounds are as low as possible. And I won't go too much into backgrounds, but just to illustrate the types of things that could cause them. One thing is there are particles that get produced in the atmosphere that can create backgrounds in the experiment. And another is that basically any material is going to have slight impurities in it that can decay and release energetic particles that can deposit energy in your detector. So even something like these copper cables, which are really radio pure and clean, will still have like slight impurities in it that can release energetic particles. So there are a few different ways that you try to get around this. One is with shielding. So this is the Majorana demonstrator. It's the experiment that I worked on as a graduate student. And this is what our detectors look like. So these germanium detectors get basically covered up here in a way that's not seen in this picture with kind of like a vacuum sealed container and put into this giant shield that weighs around 150,000 pounds. And is kind of multi-layered because there's different materials that are good at shielding against different types of particles. So this inner layer is copper, which I mentioned is something that is really radio pure. And then outer layers are lead. So you've got all these lead bricks there. But even that isn't enough for certain types of backgrounds. And this is where we get to another point that Connie brought up, is that for certain types of backgrounds, you need a way bigger shield. And the way that you get that is you use the Earth as a shield. You go underground and do the physics because you can't otherwise have a long shield. But if you go into, for instance, a former gold mine, then you can. And so this is where this experiment that I worked on is in the Black Hills area in South Dakota, the Sanford Underground Research Facility. And so you can see here, this is where the experiment was, and there's about almost a mile of rock overhead that you are just using as a shield by being down there. And so when, the first time I went down and worked on these experiments, you go underground and wear a hard hat and go basically into this mine type environment, right? This is kind of the cage is the name for this elevator ride that you take down this 13-minute long kind of open elevator ride into this cave. And, most of it doesn't look like that because you very quickly then go into lab space where things have to be very clean. But it is a weird thing that I never thought of when I was studying physics, back as an undergrad, that you would be going and working, in a mine environment. But as I mentioned, the experiment itself, things have to be really clean. And so you're in this different clean room type space. So this was me from that same trip when you actually go into the lab where the experiments are. And all that garb is not to protect me, it's to protect the experiment from backgrounds from me. And so it's not even, you get in all of these garb, but you also then, when the experiment was being built, that's not me, but you work on things in this glove box environment. So it has to be constructed in this environment to, again, protect it from backgrounds. And so people building this experiment essentially were doing it with like 4 pairs of gloves that they were working through to try to do all this really intricate thing. And then all of the materials that are used have to be really kind of specialized and carefully selected to avoid background. So a lot of the copper that was used for the near detector things was sort of like reconstituted or grown underground and then machined in an underground machine lab to kind of make it clean enough for what we needed. So I know we are getting short on time and need to move on. So I just want to kind of go back to the big picture of thinking about the perspective here and just, reminding us that science is wonderful for its ability to produce technologies that can be used for the public good. But like the thing that I am interested in it for is the sense of wonder and awe that it can give us. And Carl Sagan's always someone who has like really captured that well. And I think that's something we see easily when like looking at things like the eclipse or looking at pictures from Hubble. But that's true also when we're thinking about particle physics and kind of these other sorts of questions that science can touch on. So thank you.
We're going to take questions on Zoom first. Is there any questions on Zoom? No? Okay, we'll come back in just in case.
Okay. Please come back to us. Thank you.
So I'm wondering, with all these cuts or proposed cuts coming out of Washington, I know a lot of attention's been given to the NIH, for example, but CDC and a lot of health related. Are you also likely to be subject to cuts in the research work that you're doing and your colleagues?
Yeah, that's a really great question. And it's one that I think we are still trying to understand too, what the situation will be. I don't think we are in as much danger as some other areas of research, but I think it is still very much a concern as we look forward as to, whether we will continue to get funding to be able to do these kinds of projects. And, even if we are, there's certainly plenty of things where like, it's been really sad to see, the way that like diversity initiatives in my field are getting cut and, all of these things that are important to me, especially as like, even being a woman in physics is a kind of, thing that benefits from those programs. So, the latest news right now is that I still have a job for the foreseeable future, but like, I think it's hard to know what it'll look like long term. Like so many things, there's a lot of uncertainty that we're trying to understand the guidance on, which changes from day to day. But yeah, it's affected like everything.
Yes, thank you for gracing us with your presence and a wonderful presentation.
Thank you.
It's all impressive. So my question is a practical one. I asked a 2-part question. So first, what are the practical applications to your research and in layman's term? And I'll say that for my own personal. And then 2, I am a science fiction nut. And I like Star Trek, I like Star Wars. And so there's a lot of science language. So my question is, to what extent does actual science inform these movies, or vice versa, to what extent does science fiction inform actual science? And can it be, is it the case perhaps that actual science is trying to catch up to the movies?
Thank you for those questions. I appreciate them. I also am an enjoyer of Star Trek especially, but speculative fiction in general, although some of that is not, some of what I like fiction-wise is more fantasy or soft sci-fi, less deep on the science. But I guess to answer your first question first, the parts of science that the parts of physics that I work on are pretty indirect in terms of their practical applications. So in the same way as like, if you think about things like NASA, where eventually kind of, you can end up developing technologies that can get used in other places. I think it's somewhat similar, as we try to like do all these cutting edge detector technologies and things, some of you don't really know what the impact of those kinds of things down the line will be. It can be a little bit hard to know. And so this is kind of the weird thing about basic science is that like, there can be some applications of it, but a lot of the reasons that I am doing it are like not as application based. And so, I kind of have to figure out in my own life if there are things like teaching that give me a sense of like giving back to society in that kind of way. For the science fiction question, that is also really interesting. I kind of laugh at all the times that Star Trek references neutrinos because sometimes they're in wild ways. Yeah, I think it is like fun to see how science can be in conversation with science fiction. And I think there are a lot of scientists who, you know, enjoy that kind of thing. So yeah, I don't know, like, you know, to what degree, you know, sci-fi gives us ideas about like the next thing to work on. I think there are places where that can be, you know, I think personally, I sometimes see more the ways in which like society can be influenced by sci-fi than like how science can be influenced by it. But I think both are possible for sure.
Okay, so I tried to follow along as best as I could.
Apologies.
Thank you. Thank you for your presentation. You know, obviously brilliant. And but my question, okay, so I tried to follow along. So germanium. Then it turned into the SE?
Yeah, selenium.
Selenium. Okay.
Yes.
So when
And
you're
it's just one of the atoms within the, like you have a bunch of germanium and just one of them within it would turn into selenium.
okay, so you were saying that you're looking for the neutrinos that are potentially that you have this like really small chance that's very rare that
Of this decay, right.
of the decay.
But it's a weird one where it doesn't actually emit the neutrinos, which is strange, right? To like think about a neutrino related process that doesn't actually create any neutrinos.
Okay.
Sorry. Yeah, I'm answering questions that are not your question and making things more confusing. Let me let you ask your question.
Okay,
first.
so you were saying that the neutrinos that are coming from the sun, that like it's
Yeah.
very hard to block it.
Yes.
You're doing your best to you know, go underground and create this clean environment, but they're still getting through like the other neutrinos. So how do you tell that it's not just a neutrino that's just like floating around and that it got through and it's not, you know, how would you tell?
Yeah, got it. Good question. This is interesting because it's kind of, yeah, there were a couple different points that I brought up that are related. The particles that are backgrounds for us are mostly not neutrinos because you're right, like neutrinos could pass through all that Earth, no problem. But the nice thing about the fact that they could pass through all that Earth with no problem is that they also tend to just pass through our detectors with no problem. They've got a really low chance of interacting with your detectors. Now, there are neutrino detectors that are built underground as well, which you have to kind of have really special properties, and you still have a very low chance of the neutrinos interacting. But in our case, it's other particles that are produced in the atmosphere that would be more of a problem for us that mile of rock helps with. So for example, there's a particle called muons that are like a heavier cousin to electrons, and those would be a problem for us, whereas the neutrinos mostly aren't because they just pass through us. Thank you so much. I appreciate it.
I have two questions. The first would be, do photons have mass and can they be measured?
Photons don't have mass, but neutrinos do.
Can you measure photons?
Oh, can you measure photons? Yes, photons do interact. And so basically, like any interaction involving light is technically involving photons. Light is weird in that it sometimes behaves more like a wave and sometimes more like a particle.
The photons considered have no mass.
Yes, photons have no mass.
And you say running the experiment, you mean taking that ton of germanium, taking it down into the mine and shielding it and seeing what happens?
Yes.
Is that what you mean by running the experiment?
Yes. So, right, exactly. There's, I guess, a couple of things. I'll mention one thing. The experiment that'll have a ton of germanium, just for like correctness, I didn't mention this before, but that one will not be in the same lab space that the experiment that I worked on as a grad student was in. And so this one will be in a mountain range in Italy, which is, I know, sort of nice in that mountain ranges give you an overhead space, but you can at least drive in rather than having to go down that cage ride. And so it's a lot easier to get like a ton of material and stuff into that space.
So the one you're talking about now is not a ton of germanium, but it's germanium that's been shielded and you're watching to see what happens.
Yeah, so you've got, right, this germanium, you've been shielded, and you have to sort of connect it up to some readout system. Basically, you need a way of measuring when energy is deposited in the detector, but that's a pretty well understood technology. And so you end up hooking it up to lots of cables. You have to put some electric voltage across it. There are details to doing the detecting. But yeah, essentially it is like you have all this material and you just wait. Like it's a very passive experiment. You know, people are aware of particle physics with high energy experiments at like CERN where things are being collided into each other. And this is none of that. This is like we sit there with a bunch of germanium and wait to see what happens.
Hey.
Hi.
this is like two questions. I was wondering if scientists have been able to reconcile the unpredictable world of quantum physics with that of the more macro sphere, in which you're kind of many physicists are kind of looking at, especially when you think about astrophysics. Physics, but also how were neutrinos first discovered when they don't really interact as much, you know, with matter and stuff?
Yeah, great questions. For the first one, there are parts of it that are resolved really well. Like quantum field theory is kind of the name of where we, you know, the math and science of things that are kind of at that intersection. So we do somewhat understand the transition from like a quantum level to classical physics and, you know, what we see on a daily basis. But there are still things that are kind of missing. Like for instance, at a quantum level, we don't really understand like how gravity fits in when you get to that kind of level. So there's not like a good theory of quantum gravity at this point that's well understood. So there are still things that we're trying to understand there about, yeah, how you make that transition from like the weirdness of quantum mechanics to things at a larger level. And yeah, the neutrinos being discovered initially was a challenging thing. They were first discovered, it was actually the anti-neutrino version of things. Basically, even if neutrinos are their own antiparticle, they can sort of behave more like neutrinos or behave more like anti-neutrinos. And so the first experiment that detected them was by a reactor. And so reactors are creating a huge quantity of them in a small location, which gives you a better chance because they're, you know, you always have some probability of an interaction. So, you know, the more neutrinos or antineutrinos you have and the more mass you have for them to interact with, the better. And then the solar neutrinos were first detected, actually it was in the same lab space as the experiment that I worked on in a grad student was where the first solar neutrino detector was located. And it's like this interesting experiment that I don't remember all the details of. It ended up using like this giant vats of liquid that had a decent chance of interacting in it. But it has a lot of the same challenges of the kinds of experiments that I work on, where you have to make your backgrounds from everything else really low and just have a lot of mass so you have a decent chance of an interaction happening.
We got one more question online to take, and it says, how long would you expect, believe it might take for something to happen with the germanium, since this is such a passive experiment?
Yeah, that's a great question. And some of it is, you know, we don't know exactly, like, if this thing really happens, we don't know what the exact half-life would be. We have limits on what it must be more than. So it kind of depends what the half-life ends up being. So you could end up, you know, we could see something in the next year of running, or it could be something that takes a decade for us to see, you know, you wouldn't be able to tell it with just one event because there are still some backgrounds. You need to build up at least a couple to have a chance of seeing like a peak in your spectrum is essentially what you're looking for. So it is a very kind of long scale experiment. And, you know, you can do things to like, we see the standard model version that I mentioned earlier, where you do have the neutrinos being emitted, that we see pretty frequently. And that still has a very long half-life. The half-life of that is like 10 to the 20 years. And that that's one of the most common things that happens in our experiments, which is kind of wild, but you've just got enough germanium that that's true. So the thing that we're looking for is, yeah, it's very much a long-term game. It's very much a thing that you have to be waiting for years and years. And that's something we didn't necessarily always know going in. Like, you know, this is kind of a thing that has taken a phased approach. And so, you know, the experiment that I worked on as a grad student was using like, you know, more like 30 kilograms of detectors rather than a ton. And we still thought it was possible you could see something with that because we just didn't know exactly what the half-life would be.
So Anna, thank you. I especially enjoyed your combination of expertise and enthusiasm. And I mean, as we leave today, do you want the group looking for missing antimatter? All right, well, keep our eyes, and I'm very impressed with this group, just the number of really good questions we generated. So Anna, in honor of your program today, the club will make a donation of $100 to the quarter to the warehouse. Lots of people made this possible today, so I want to thank Natalie, Sue, Sam, Connie, Joy, Tim, Alan, Michael, Isaac, and then also Tyler made an appearance to help today. So thank you all. Next week, Change of Pace will be upstairs in the Georgian room, and our speaker will be Maria Talbert with the IU Auditorium. And now, if you're able, please stand for the rotary four-way test. Of the things we think, say, or do, first, is it the truth? Second, is it fair to all concerned? Third, will it build goodwill and better friendships? Fourth, will it be beneficial to all concerned? And fifth, is it fun?